Random AP Precalculus problem from section 1.1. The function g of x is defined on the interval 0, 8, like so. Based on the values in the table, where is the function increasing? Now, the function increasing just means that if you have a picture, it's going to go up and to the right. It has nothing to do with concavity. So we only care about where this function is increasing. So it goes from -4, -3, -2, and then stops. Then all of a sudden goes down. So there's an increase right there. Then from here to here, it decreases some more. Now we go from -6 to -3. It's increasing, and then stops again. So here's our intervals of increase. So from 0 to 2, boom, and from 4 to 6, boom, 1 and 3, 1 and 3, A is my guy. For what values of x is the rate of change decreasing for the function shown below? First off, this is saying rate of change decreasing, not function decreasing. When your rate of change is decreasing, that implies concave down. So it looks like it probably starts out at concave down right way over here at -4, or maybe -infinity. It all depends. And it stops its concave down at 0. So we will say, let's assume that this is going on forever, just for example's sake. Let's say -infinity to 0. And that appears to be it. Several coordinate pairs from a linear function are shown in the table. I see. What is the average rate of change on the interval from x equals 21 to x equals 102? All right, well, rate of change is the formula f of b minus f of a over b minus a. I can call you A, I can call you B. It really doesn't matter. So you'll be A, you'll be B, you'll be f of A, you'll be f of b, and now it just becomes a nice little PEMDAS problem. F of b is 28 minus f of a, which is 1. Spoke too soon. B is 102 minus a is 21. 28 minus 1 is 27. 102 minus 21 is 81. Those are both divisible by 3, so let's divide. Those are both divisible by 9. So let's divide the top and the bottom by 9. Those are both divisible by 27. Oh my gosh, so that actually just becomes 1/3. Oh, look at that. Look at that. Oh, wasn't that fun? That was a lot of fun. Random math problem for 1.2. In their first season, a basketball team practices for 45 minutes per day and makes 199 free throws. The next season, they practice 55 minutes per day and they make 240 free throws, which is true about the rate of change from the first to the second season. So let's actually find the rate of change. Here's the formula for rate of change, f of b minus f of a over b minus a. Now, in this case, a could be 45, which means when I plug in, quote unquote, 45, I get out f of a, which is 199. So b would be 55, and when I plug in b, I get 240, which is f of b. I know you can barely see that, but you get the idea. So f of b is 240 minus f of a, which is 199, over 55, which is b, minus 45. So what, 241 over 10 rounds out nicely to 4.1 or 4 if we're rounding. So let's figure out what we're supposed to do. The rate of change is negative. No. The rate of change is positive since the free throws were all positive numbers in both seasons. Well, free throws are always going to be positive, so that's not why it's positive. You're not going to have negative free throws. It's ridiculous. The rate of change is constant since the practice time and the number of free throws is both increased. That's not necessarily true. The rate of change is positive since the practice time and the number of free throws both increased. That's my guy. So even though some of these has some truths to it, it's not completely true like D is. And even though I didn't have to do that much, I did it anyway, and it was fun. So much fun. Section 1.2, rate of change. A quadratic function has the equation y equals, it's factored, x plus 2, x minus 3. When comparing the rates of change at the points x equals 2 and x equals 3, which statement is correct? Now, thing number one, it mentions rates of change. It mentions nothing about average rates of change. So if you're thinking f of b minus f of a, stop it. Thing number two, this is a calculator problem. So let's pull up a picture of what you see on the calculator. Now, what I'm doing here is rate of change is another fancy word for slope. So it's asking me, what's my slope going to look like at x equals 2, there, and what's my slope going to look like at x equals 3? Well, at x equals 2, I can't tell exactly what it is, but I have a positive slope. What I do know is that x equals 3, right here, that slope is steeper. Now, how do I know that? This is concave up. And when it's concave up, the rate of change is always increasing. So what I can say is the rate of change for 3 is greater than the rate of change for 2. The rate of change is greater at 3 since 3 is greater than 2. That's true in this case, but not necessarily true, so I'll put a question mark right there. The rate of change at x equals 3 will be 1 more since 3 is 1 more than 2. I don't think that's the case. By using x values close to 2 and x equals 3, the rate of change is greater at x equals 2. That's not true. By using x values close to 2 and x equals 3, the rate of change is greater than at x equals 3. I guess that would be true. Although A is technically correct in this case, A is not always true, so we can't select A. So in this case, B is true because I can use these points. But I just used a picture and I used common sense. I'm not going to go to second table and try to get values close to 3. You could, but I'm not going to do that. Selected values of a function f are shown in the table below. Okay, hello table. Suppose n is equal to the average rate of change in f on the interval 0, 4. So let's quick do that. Okay. N is equal to the average rate of change. So n is going to equal f of b minus f of a. So you would be like my f of b, you would be like my f of a over b minus a. So f of b is 0, minus f of a is negative 8, so I have a double negative there, over b, which is 4, minus a, which is 0, so that's going to be double negative 8 over 4, and it's 2. Okay, got n down. P is equal to the average rate of change of f over interval 610. It's funny, NP are my initials and 610 is my area code. So you would be my new f of a, and you would be my new f of b, and you would be my new a, and you would be my new b. So P would equal f of b, which is negative 40, minus f of a, which is negative 16, over b, which is 8, minus a, which is 6. Negative 40, double negative becomes a positive, so we got negative 24 over 2, and that becomes negative 12. So n was 2, p was negative 12. Which of these could be a true statement based on the values of n and p? The function f could be a linear function because n equals p. Well, that's not even close. The function f of x could be a linear function. It's not linear. I know it's not linear because the rates of change are different, so I'm not even going to bother. The function f of x could be quadratic because n equals p, but n doesn't equal p, so no. The function f of x could be quadratic because n does not equal p, which is true. So if it's quadratic, the rate of change is always changing. This is asking for rate of change, and the rate of change is changing or has changed. So yes, this could be quadratic because the rate of change is not the same. Okay, random AP Precalc problem from section 1.3. A portion of this graph right here, it's a quadratic function, as you can see, is shown below. On the interval 6, 10, which is 2, 4, between, I know the numbers are hard to see, 6, 10, the function g has an average rate of change 2 times its average rate of change on interval 2, 4. Okay, so here's 2, 4. And I'm gonna zoom in a little bit so I can see okay, so here we are. So I don't even know what it's going to be asked. I'm just zooming in. Hopefully my screen adapts well to this. This average rate of change that I have here in red is going to be 2 times the average rate of change in blue. Now I could do the f of b minus f of a formula to do the average rate of change, but I've done that in several other videos. I'm not going to do that here. I'm going to make life easier. Average rate of change is just fancy talk for slope. So the slope of this blue line is going to be, you know what, since I don't even have a nice graph, I might as well just do it. F of b, I feel wrong doing it, but I'm doing it. F of b minus f of a over b minus a. So it would be something like 12 minus 6. Okay, so like it looks like I would go up 6 over 2. So I'm just actually going to do that, up 6 over 2. That's what it looks like. So the slope is 3. Yippee. 12 minus 6 is 6. 4 minus 2 is 2. The average rate of change is 3. Okay, boom. Now, the red guy is supposed to be 2 times that. And if you're like, well, why can't I just do the same thing that you did for blue? Well, because that's a C right there. So I don't know what C is, and I have a feeling that's what I'm supposed to do. What I do know is I know that the average rate of change for red is supposed to be 2 times blue, which means the average rate of change is going to be 6. So if I have, let's do this. Let's actually set the whole thing up. And I'm going to have fun with this. C minus 22, I'm using this formula right here because I have a feeling that I'm supposed to do find C. Yep, find the value of C. There it says right there. So I'm going to zoom up again so I can have everything in front of me. I'm supposed to find C. So there's other ways that you could do this. I'm just going to whip out the old formula again. Okay, f of b minus f of a. I don't know why I put here. That looks like a C. F of b minus f of a over b minus a. So C minus 22 over 10 minus 6 is supposed to be 6. Okay, C minus 22, no clue. But it's going to be over 4, and it's going to equal 6. Multiply both sides by 4. Good old Algebra 1. C minus 22, the Taylor Swift special, equals 24. Let's add 22. And 22 plus 24, and let me write it big out here so when I zoom out I can see it, is going to be 46. C equals 46. So let me zoom back out, get everything on the screen. C is 46. Find the value of C, 46 right there. 46 right there. Yeah, kind of a weird problem. Very weird indeed. This is the way I did it, though, and there's probably other ways that you can do it, but this one would be considered on the difficult side, I suppose. Consider the function f of x shown on this graph below. On which of these intervals could f have an average rate of change of -2 and have the rates of change that are changing at a rate of -2? So let's break this down into simpler terms. Okay, it has the average rate of change of -2 is fancy talk for slope is -2. I'll just write out slope is negative for now. And the rates of change are changing at a rate of -2. What that implies is if the rates of change are changing at a -2, that implies concave down because the rate of change of the rate of change is negative. Okay, the rate of change of the rate of change is negative. So I need a negative slope and I need concave down. Now, before I even look at these options, let's find out where we have concave down. So none of you, 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 inflection point. Now, this is completely concave down. However, I want negative and concave down, so none of you, and that appears to be the maximum value right there. So the only area that appears to have a possibility where on any interval I have a slope of -2, so, I'm sure somewhere on this interval I can draw a slope of -2, and the rate of change is changing at a rate of -2, which means the rate of change is decreasing, which means concave down, is from this area to this area right here. G and H is the only option that I have. So that's going to be my guy. So this is a very bizarre sounding problem. It's a very bizarre setup problem. But again, it's telling you negative slope, rate of change is decreasing. I have to be careful how I word that. GH is the only guy that seems to do that. Which of the functions shown in the table below could be quadratic? So before I even get into this, I'm going to have to zoom up because these pictures aren't that great. Okay, if I were to take a table and find out all of these numbers are the same, that would be linear. If they're not the same, then step number 2 is do it again. If all of these numbers are the same, that would be quadratic. That's what I'm looking for. I'm going to go to each table. I'm going to zoom in. I'm going to go to each table and see if the rate of change is the same. And if that's the case, then that's the one I want. So let's take a look at A. Okay, in each case, I add 2. Now, these guys are going up by 2. These guys are going up by 2 each and every time. So this guy right here is actually linear because the rate of change is constant over consecutive equal length input value intervals. I think I nailed that phrase right there. Now let's try this guy. You go down by 3, down by 3, down by 3, down by 3, down by 3. You too, my friend, are linear. Okay, so not you. Let's zoom up. Let's zoom up. Let's try you. I'm going to subtract 1, subtract 2, subtract 3, subtract 4, subtract 5. You are not linear because these numbers are not the same. So let's see if the rate of change is the same. You go down by 1, you go down by 1, you go down by 1, you go down by 1. So this guy is my guy. That's my quadratic equation because the rate of change of the rates of change over consecutive equal length input value intervals are exactly the same. Wow. Zoom out. Circle. Good job, everybody. A polynomial function has zeros at -2 and 0 and 1, 0. These are points, not intervals. Which of the following must be true? So I see words like minima and stuff like that. I kind of know what's going to happen. Let's draw ourselves a coordinate plane. So that's a perfect line. I have -2, 0, boom, and I have 1, 0. And I know you are a 0 and you are a 0. Now, usually when these things happen, if we're talking about max, min, stuff like that, I don't really care what the line looks like. It's telling me it's a polynomial, which means, something like this could be happening, or it could be something like this happening. We don't have that information. But what we do know is that if these are 2 zeros, we are guaranteed some type of maximum or some type of minimum, even though I drew that in opposite ways. We're guaranteed some type of that. So the fact that there is no 0 has nothing to do with it, or there is a 0, that doesn't have to be true. We don't have to have a 0 in between our zeros. There's a local minimum or a local maximum, or there is a global minimum or a global maximum. We'll talk about that in a little bit. There is an asymptote, no. So the rule states that there is going to be a max or a min, and the rule states that it has to be local. Now, if you're wondering why not global, or why not an absolute maximum or an absolute minimum, it's because, we don't know the exact behavior. Okay, we don't know the exact behavior of these graphs to guarantee an absolute anything. We can, though, guarantee a local something, and that's why we go with A. So it's a very tricky problem, and it's one of those things where you have to be really, 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 really good to guarantee your answer, but A is the only thing that must be true. You're very rarely guaranteed absolute or global anything, except for global domination by me. Like and subscribe. All right, so we've got ourselves a random calculator problem. Consider the polynomial function x cubed minus x minus 2x squared plus 2. Which of the following occurs at approximately x equals 0.67? So I'm going to step to the side. I'm going to let the calculator do the job, come back, and see what happens. Okay, so I'm supposed to graph this guy right here. I already typed it in because, saving some time. When I go to graph, it gives me a nice little cubic right there. And I care about what happens at 0.67. Now, at 0.67, I really can't see it that well. So what I can do is I can zoom in by hitting zoom 2, hitting enter, and I can kind of see what happens at 0.67. If that's not good enough for you, you can hit second calc and calculate the value at 0.67. Now, what we see appears to be a change in concavity, which is what happens when I go to the dentist. At 0.67, it looks like an inflection point. So let me answer the question based off of what I see here. So basically what you saw is a picture that looks like this. When we found the value at 0.67, it gave us that which appears to be an inflection point. And in this case, an inflection point takes us from going concave whatever to concave whatever. And in this case, it goes from concave down to concave up. And so that's our guy. The graph of which of the functions intersects the x-axis at 4 different points. So looking at the pictures that I have, I know what I'm looking for is some kind of function that looks like this, 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 and this, where all of these are different. Because you're looking for something to go through 1, 2, 3, 4 times, something like that. All right, so first things first. We need 4 different points. First things first, u can be factored a little bit more. So technically, this guy is x times x plus 1 times x minus 1 times x plus 1 squared times x minus 2. So what that does is that gives us a 0 at 0, a 0 at negative 1, a 0 at positive 1, a 0 at negative 1 with a multiplicity of 2, and a 0 at 2. Well, I'm not going to say negative 1 and negative 1 and negative 1. So this guy goes through, for sure, 0, negative 1, 1, and 2. Well, I'll be darned. Isn't that 4 different points? My answer is A. Now, if you're looking at B and you're thinking, why not B? Well, B only goes through 3. And this guy, technically, if you were to try to factor that, you can't. And if you were to try to solve that, set it equal to 0, thinking zero product property thoughts, you would get a complex number because you would subtract 1, get negative 1, and try to take the square root of a negative number. Can't do it. That's complex. So this one only has 1. So definitely not B. If you're looking at this one and saying, but this one, sir, has 4 parentheses. Yep, and 2 of them repeat. So not you. This one has the same issue as this one. And even then, you have 0, you have negative 3. You set that equal to 0, you would get x squared, subtract 3 from both sides, take the square root, you get more complex numbers. So it's definitely A. Right off the bat, we have something nice. A polynomial function is given by p of x equals x plus 2, x minus 1, all of it squared, and x plus 5. What are all intervals on which p of x is greater than or equal to 10? 0, not 10. So what I'm going to do is I'm going to make myself a sign graph and find out where the magic happens. Now, I'm just going to rewrite this out over here because I need the space. X minus 1 squared, x plus 5. I have 3 distinct zeros. I have negative 2, I have positive 1, but the multiplicity is 2, and I have negative 5. So let's write those zeros out. Negative 5, negative 2, 1 in left to right order. Now, what I also have is I have x times x again times x. What I am doing is I'm finding out, is this a cubic? Is this a quartic? Is this a quintic? What am I finding out? If you multiply the leading term in each factor, and if you have a multiplicity, you multiply that out that many times, you get x times x times x times x, which is x to the fourth. So this picture is going to look something like that. So now let's graph it. If I'm making a sine graph, I'm going to start from the very top. It's going to go through -5 because the multiplicity at -5 is odd. It's going to go through -2 because the multiplicity at -2 is odd. It's going to approach 1 and bounce off of 1 because the multiplicity is 2. So when the multiplicity is odd, you go through that 0. When it's even, you bounce off. So what I have is I have several areas where my polynomial is greater than or equal to 0, which means it's above my sine graph. So it's above my sine graph from -infinity to -5. And since we include 0, we're going to include -5, union. And then it's underneath between -5 and -2 and shows back up above again from -2 going on forever. So we're not going to say -2 to 1 and then 1 to forever. We're just going to include -2 and go all the way on forever. And that gives me C. Given the table of values, determine the degree of the function. We've done these before. This is the one where I make sure that these guys go up by the same number. They do, consecutive equal length input value intervals. And then I have to test to see if these guys go up by the same. Doesn't look too promising at first. So I'm going to pretend that I didn't do these numbers ahead of time because I have a potential to screw these up. 10 to -3 is -13. -3 to -84 is -81. -84 to -305 is -221. -305 to -762 is -457. And then last but not least, we got ourselves -813. So it's not linear. That wasn't even an option anyway. So let's test to see if it's quadratic. Does the rate of change of the rates of change stay constant, or do these change too? So to get from -13 to -81, I subtract 68. To get from -81 to -221, I subtract 140, so it's not quadratic. To get from that number to that number, we subtract -236. And then from one number to the next, we subtract 356, making it not a quadratic. Then let's do it again, see if it's cubic. Okay, so to get from -68 to -140, we subtract 72. To get from this number to the next number, we subtract 96. And to get from this number to the next number, we subtract 120, not cubic. Let's see if it's quartic, if it's a fourth degree. To get from -72 to -96, we subtract 24. And to get from this guy to that guy, we subtract 24. And oh, happy day, it's a quartic, making it a fourth degree polynomial. The graph of the non-constant polynomial right there is shown above. Which of the following describes the end behavior of P? So end behavior is limit. Okay, and as we can see, they want us to write it out as limit. So let's find out what the limits are. When you move to the left without bound, you are trying to find the limit as x approaches -infinity. The limit as x approaches -infinity has my graph going upward, which means it is positive infinity. Similarly, if I move to the right without bound, I'm asking you the limit as x approaches regular infinity because x is getting bigger, and y also happens to get bigger, so both of my limits are going to be infinity. So the limit as x approaches -infinity is -infinity? Nope. The limit as x approaches -infinity is infinity? That's true, but that's only half of it. The limit as x approaches infinity is -infinity? Nope. The limit as x approaches infinity is positive infinity. That's true. But also the limit as x approaches negative infinity is negative infinity. That's not true. So B's got to be my guy. Even though it seems a little incomplete, that's going to be the one I'm going with. The function p is given by p of x equals negative x to the 6th plus 2x to the 8th minus 3. Which of the following describes the end behavior of p? So what I need to do is I need to take a look at this guy and try to figure out what my graph looks like. If you're looking at negative x to the 6th and thinking, that is a negative function, x to the 6th, you're doing it wrong because that's not the leading term. You are the leading term. And since this is a positive, x to the 8th, it's an even degree. You are going to start at the top, a bunch of stuff happens, blah, 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 who cares? And then you end at the top as well. So as I move to the left, my limit as x approaches negative infinity, which is decreasing without bound of, what is this, p of x, is going to be moving up. My limit as x goes to the left is going up positive infinity. My limit as x approaches the right without bound, approaches positive infinity, is also going to be positive infinity, which appears to be u. So be careful about that leading coefficient stuff. That's serious business. The figure above shows the graph of a polynomial function h. Which of the following could define h? Okay, so it's just giving me a bunch of polynomials, not allowed to use a calculator, so this is the no calculator version. What I have is a cubic, because I have one bump, two bumps. Since it starts from the top and ends at the bottom, my leading coefficient has to be negative something x to the 3rd. So that's got to be my leading coefficient. So does this give me a leading coefficient of negative something x to the 3rd? No, you're positive, which looks like that. Does this give me a leading coefficient of negative something x to the 3rd? Yup. Does this give me a leading coefficient of negative? No, that's x to the 4th. That's going to look more like the w. And this is a negative x to the 4th, an upside down w. No, no, no. B, baby. B is for baby. Okay, let's look at this random problem from AP Precalculus section 1.4. A polynomial function increases from negative infinity to 1, that's an interval, and decreases from 1 to infinity. Which of the following must occur? So this is not that bad of a problem at all. So if I had a coordinate plane, right, I'm just going to draw this out because this problem won't take much longer. At 1, I have some polynomial. All I know, I don't know what it looks like, but all I know is it's increasing. And then once it hits 1, it starts decreasing. And I don't know what it looks like, and I'm purposely making it look bad. So it's asking what must happen between 0 and 2. So here's 0, and here's 2. What must happen is I'm going to have a maximum. So what must happen? I am going to have a y-intercept. Actually, no, I guess I don't have to have a y-intercept. Technically, I could start this way down here, so I don't need to have a y-intercept. I don't need an x-intercept. Even the picture that I drew doesn't have one. It's not going to have a local minimum, but what it must have is a local maximum. Basically, there's a rule that says if you go from increasing to decreasing, right, you're going to have a local maximum no matter what. I drew it out just to drive home the point. It's a point, get it? Like and subscribe. Which of the following statements is true about the function f defined above? All right, f is always increasing, f is always decreasing, x approaches them. Okay, so this is 1.7. We're dealing with rational functions, and what we have upstairs is a function with a degree of 1. What we have downstairs is a function with degree of 2. Now, specifically, if you really want to get into the nitty-gritty of what's going to happen, you always take the leading coefficient of the numerator over the leading coefficient of the denominator. And the way I can find the leading coefficient of the denominator is I can multiply the leading terms of each factor. That happens. Okay, so this is going to be the behavior of this graph. It's talking about approaching infinity, always increasing, always decreasing. Look, we have something like this going on. It's not going to be always increasing. It's not going to be always decreasing, especially when your degree on the bottom is higher than your degree on the top. It's not going to happen. So we need to talk about limit. All right. In this case, if we are asked to find what happens when the limit as x approaches infinity, what we do is we simplify this guy the best that we can. So we are being asked to find the limit as x approaches infinity of 1 over x. What's going to happen realistically with this guy is as x gets larger, this guy approaches 0. For example, if I were to plug in 1, I'd get 1. If I were to plug in 10, I'd get 0.1. If I were to plug in 100, I'd get 0.001. And as x gets really, 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 really big, we are going to get a really, 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 really small number, which is 0. So as x approaches infinity, the denominator of the function increases at a faster rate than the numerator. Yup. And as x approaches infinity, the numerator of the function increases at a faster rate than the denominator. Nope, because the numerator is smaller than the denominator. C is going to be my guy. I did more than I had to, but I'm glad I did it because I had fun. For the rational functions shown below, the values of a, b, m, and n are positive whole numbers. I hate these problems. It is known that as values of increasingly large magnitude are input for x, in other words, that as the limit of x approaches infinity, the graph of the function approaches the horizontal asymptote y equals 1/2. So if I were to look at this graphically, there's a very bland coordinate plane. We have a horizontal asymptote at 1/2, which means my graph, whatever it looks like, it could look something like this. My graph is never going to touch a half, and it's going to hit a limit of 1/2. Now, the only time that you're going to have a number that is the limit as x approaches infinity is if the degree upstairs is the same as the degree downstairs. In other words, m and n have to be the same. So which of the following statements must be true? M must equal n, okay? Now, as far as the others must being true, none of these have to be true. If m equals 2, that's great. You can then say, well, then n could equal 4. How about that? So, you're disqualified now. 2a has to equal b. Well, no, a and b doesn't really matter as long as the degree upstairs and the degree downstairs are the same. Now, I take that all back. Because now looking at this, if this approaches 1/2, if this approaches 1/2, then what's going to happen as I plug in the limit as x approaches infinity is there must be a before step going on here. And that before step has to be like I get 1 up here over 2, and maybe I have x to the 4th, and maybe I have x to the 4th, and then these cancel out, and I get 1 over 2. So what's going to happen is a has to equal 1, and b has to equal 2. In other words, 2 times a has to equal b. So 2 actually does have to be true. So at first I was like, nah, but then I remembered that this 1/2 actually has a lot to do with it. So 2 and 3 only have to be my guy. A is optional, but 2 and 3 have to be my guy. Kind of a tricky problem. I find this very difficult. It actually threw me off for a second there, but I picked myself up at the very end by my bootstraps. For the rational functions shown below, the value of a and b are integers, so we don't know a and we don't know b. We have an n there. Okay. It is known that as values of increasingly large magnitude are input for x, in other words, the limit as x approaches infinity, the graph of f approaches the line y equals 3 over 2. Approaches the line y equals 3 over 2. So we have ourselves a horizontal asymptote, y equals 3 over 2, and all the magic happens at 3 over 2. So this is what's got to happen, right? I'm going to take a before step. What must happen is n and n are the same. These guys have to be the same degree. We know that. That's why it doesn't tell us anything for n. So let's just make believe that n is 8. Okay, I care about the leading coefficients. The leading coefficient up here is a x to the n or x to the 8 or whatever, and the leading coefficient down here is negative b x to the n. Now, in order for us to hit a horizontal asymptote, these have to be the same. I don't know why I put 2 there. These have to be the same. These cancel out. Now, what happens is since x approaches infinity and I'm left with just this fraction, like so, the limit part doesn't really matter. And a over negative b has to end up equaling 3 over 2. Okay, so which of these could be the values of the constants of a and b? All right, well, if a is 6 over negative b is 4, that gets me negative 3 over 2, which is not 3 over 2, not what I want. If I try out a is 6 and negative b is negative 9, that gives me 6 over 9, which is 2/3. Not the same as 3 over 2. Not what I want. Next option is if a is negative 12 over negative b is regular 8. That simplifies to negatives cancel each other out. 3 over 2. That is what I want. So C is a possible answer. It is impossible to listen, nothing's impossible with the Lord. And if you know that the value of n is, if they're the same, then it's fine. It doesn't matter. As long as the degrees are the same, you will approach a horizontal asymptote for a limit, and that's what we get. So C is my guy. The graph of a rational function f of x is shown above. Ooh, look at it. The graph shows that as increasingly large values are substituted for x, increasingly large values are substituted for x, is just fancy talk for x approaches infinity, the graph approaches the horizontal line y equals 2. So what are we talking about? F of x equals 2. Which of the following is true? Okay. I'm not sure what the point of this problem was. I literally just did it. Maybe this is supposed to be much easier than it's supposed to be, but I mean, we could see from the graph that as x approaches infinity, you get 2. We could see from the description that as x approaches infinity, we get 2. So A is my guy. That was a simple one. The rational function has a slant asymptote parallel to the line defined by u. All right. First things first, if it has a slant asymptote, then what we have is a rational function, and so it wants to give us f of x, and whatever the degree is up here, it's going to be 1 more than whatever the degree is down here. Okay? Now, also, the slant asymptote is defined by y equals 2x minus 1. Oh, it's parallel to that. Ugh. So what's going to happen is whatever my slant asymptote is, it's going to have a slope of 2. We don't care about the rest. So this is what we need to do. First off, what we need to do is we need to eliminate the ones where my degree in the numerator is not 1 more than my degree in the denominator. So if I look at each one of these individually, you have a smaller the degree than that, no good. You have a degree of 3, you have a degree of 3, no good. You have a degree of 3, you have a degree of 3, no good. You have a degree of 3, you have a degree of 2, it must be you. Now, usually what happens with these is you are asked to find the slant asymptote, and the way you find the slant asymptote is you do polynomial long division, and your solution to the polynomial long division, not worrying about the remainders, is going to be your slant asymptote. Now, I don't have to do this whole thing because I will stop after step 1. Now, when you do polynomial long division, you're like, 2x squared times what is 4x to the third? Well, 2 times 2 is 4, and x times x squared is x cubed. And then usually you do the whole thing and you subtract and you do the whole thing. But in this case, I can be done because my slant asymptote is going to be y equals 2x blah, 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 which is supposed to be exactly what I get. So D was a lot easier because I was able to eliminate A, B, and C based off of this fact. But if I had to go one step further, polynomial long division would be required, and we would still come up with the same answer. Fun. The rational function f of x is x minus 8 over x plus 2, and it's defined over the interval there. Well, why does it say that? Because of you. Determine the interval on which f of x is positive. Oh, I like these. First off, this is what we need to do. Okay, we are going to draw a rough sketch of this because this guy is friendly enough. Magic happens in one specific area and then another specific area. Area number 1, magic happens at the vertical asymptotes. Vertical asymptotes exist at the vertical line that makes the denominator undefined. If I were to plug in -2, if x was -2, that would make the bottom 0, so that is a vertical asymptote. So if I were to begin, drawing a picture right now, what I know is this: at -2, vertical asymptote, my graph isn't going to touch either of that. Thing number 2 that I need to be cognizant of is, sorry, getting another color. I care about the zeros. The zeros, where my line crosses the x-axis, where there's a change in positive versus negative, is just going to be one of them, and that's where the denominator is 0. So if x minus 8 is 0, then x equals 8 is going to be a 0. So way over here at 8, my line is going to cross the x-axis. Okay, so in one of these cases, I have a picture where nothing touches and I have one that goes through. So let's try to draw what we think is going to be a rough draft of what's going on. What we have is a function that behaves like x over x, which looks like this. Okay, so the picture that we're going to have, and another thing that I have to keep in mind, this was a close one. I also care about end behavior. Since the degrees are the same, the end behavior, the limit as x approaches either infinity, can be described as x over x, which means 1. So I'm going to have a horizontal asymptote at 1. So let's draw this out. Not that that's going to affect too much, but that's going to help us understand why our answers are going to be what they are. So the picture is going to look like this. This is my graph now. And then it's going to hit the vertical asymptote, start back down, go through 8, and then level out at 1. So now what I'm going to do is I'm going to make myself a sign chart. Okay, magic happens at -2 and at 8. From -2 to the left, I have a positive value because everything is above the x-axis. Between -2 and 8 and not including, everything happens below the x-axis. And then once we hit 8, it jumps back above the x-axis. We care about what's going on above the x-axis. We're not going to include what happens at the x-axis. So when we have our intervals, we're going to not have brackety-looking things. We're going to have parenthesis-looking things. And my parenthesis-looking things are going to be from -infinity to -2, union, and from 8 to infinity, which is u. Now, if this was done on a calculator, life would be easy, but it's not. So with these, we, fortunately, we're given one that's not the end of the world, and we're able to remember that, all right, well, this is just a regular rational. If a regular rational is going to look like that. But you have to keep in mind vertical asymptotes, zeros, the horizontal asymptote. If you're wondering why was that important, well, it helps us understand that this guy is never going to go underneath and this guy is never going to be far above. So that helps us. Like the question could be is, well, how do we know that this guy doesn't go down and eventually past the x-axis? Well, because it's never going to go past the horizontal asymptote. So lots to deal with there, but we did it. Fun. Given the rational function f of x equals blah-de-blah over blah-de-blah, which of the following is a real zero of the function? So whenever you're being asked to find the zeros of a rational function, you only care about the numerator being set equal to 0. So let's take 3x cubed plus 6x squared minus 45x and set that equal to 0. Let's factor out a 3. Let's factor out an x. That leaves us with x squared plus 2x minus 15 equals 0. 3x is still there. What two numbers add up to positive 2 and multiply out to negative 15? Well, plus 5 and minus 3, of course. So our real zeros are going to be when u equals 0, so 0. When x plus 5 equals 0, so you would subtract 5 and get negative 5. And when x minus 3 equals 0, so you would add 3 and get 3. Those are our real zeros. So 0, negative 5, and 3. 0, negative 5, and 3. So all of them. Okay? So it's worded weird because it makes you think that you only need to find one. We found 3, and 3 was what we cared about. And so we got 3, and that was fun. Fun. Which of the following equations has the same real zeros as the function in the graph below? Well, here's my function, and it crosses the axis here at negative 3, and it crosses the axis here at 1. So the real zeros for this guy are at negative 3 and 1. So what I need to do is I need to find which one of these has the real zeros of negative 3 and 1. When you're being asked to find the zeros in general, you only care about the numerator. So for A, we could test out x squared plus 2x minus 3. That factors out to x plus 3, x minus 1. And if our job is to find the zeros, we set it equal to 0. You would be negative 3. You would be positive 1. You're my guy. Now, if you wanted to test out the others, hey, be my guest. But you don't have to because we already came across our answer pretty quickly. The rational function f is defined above which of the following statements are true. So we have a rational function. It's talking about wholes, domain, and real zeros. So I hate these. We have to factor the equation upstairs. So 3x x minus 1 plus 3. Let's double check. 3x times x is 3x squared. Plus 9x minus x. Good. Okay, good. And then we have x plus 3 on the bottom. I probably should have guessed that that was going to happen. All right, what do we care about? We care about wholes, domains, and the amount of zeros that we have. So the whole is going to be where does my rational function have a repeating parentheses, one upstairs and one downstairs? Well, right here and right here repeat, which means my whole is going to be the number that makes this 0. So x equals negative 3 is a whole. Check. The domain of f of x is the set of all real numbers. Well, here's the problem. You might be thinking, don't these cross out? They do and they don't. Okay, they do and they don't. And the problem is with this guy, the original problem had x plus 3 in the denominator, which means you're not allowed to plug in negative 3. You're not. So my domain is going to be everything except x cannot be -3. So is it all real numbers? Nope, because all real numbers includes -3, and you're not allowed to include -3. Here's the tough one, the zeros. The zeros are, what numbers can I plug into the original equation that give me a 0? Well, I would plug in 1/3, and I would plug in -3, but here's the thing, you're not allowed to plug in -3. So technically, -3 is not a 0, because if I were to graph this, there ain't anything going through -3. It's not going to happen. So I only have 1 0. So that is true. So 1 and 3 are both my guys, and my answer is C. The graph of f is shown below. Which of the following statements about f is true? All right. So it talks a little bit about limits, it talks a little bit about zeros, and it talks a little bit about limits. So first things first, this right here is saying, and let me zoom up a little bit because this, picture is not that great. Meow. Meow. This is saying the limit as x approaches -7 and then has a little positive symbol that you can barely see. X approaches negative symbol with a little positive, -7 with a little positive symbol. What that means is from the right. So asking, or A is asking, is my limit as x approaches -7 from the right side the same as my limit as x approaches -7 from the left side? Well, from the right side, it's approaching infinity, and from the left side, it's approaching -infinity. So that's a big NO to you. B is asking the limit as x approaches 3, and that's a little plus from the right side, equals infinity. That is true. So let's just make sure that the other two aren't. F of x has no real zeros. Well, there's a real 0 right there, so that's not even close. The limit as x approaches infinity does not exist. Well, yeah, it does exist. It looks like it's approaching 0. So yeah, B's our guy. Determine which of the following functions has a graph with a vertical asymptote at x equals 5. All right, so we have rationals. Vertical asymptotes exist when you have, and if it's going to be x minus 5 or x equals 5, they exist at x minus 5 on the bottom, and you may not have x minus 5 up top. Okay, so that's the only place where that's going to happen. A says x minus 5 over x squared minus 25, which is x plus 5, x minus 5. Oh, look, an x minus 5 on the top. Can't be a 1. Okay? 2 is x over x squared minus 25. So x over x plus 5, x minus 5. So there's an x minus 5 in the bottom and no x minus 5 on top. So 2 seems to do the job. And 3 is going to be x plus 5 on the top, x minus 5 when I factor that out. And on the bottom, you have x minus 5, x minus 5. So after these cross out, you are still going to have a vertical asymptote at x minus 5 on the bottom, which tells me it's going to be 2 and 3 and 2 and 3 only. Fun. Which of the following lines is a vertical asymptote of f of x equals x squared minus 2x over x plus 1? Well, I have x plus 1 on the bottom. So unless I have x plus 1 on the top, which I don't, because if I factor out x, I have x minus 2, my vertical asymptote is going to be the x value that makes the bottom 0, so x equals -1 is my one and only vertical asymptote, which is A. Pretty simple, pretty easy. A graph and equation of the function f of x are provided below. So here's the graph, here's the equation. I have a little b stuck there, so that's no fun. What is the value of b? Well, let's see what we have. Okay, I have no restrictions on the bottom. So what I'm going to do, since I'm dealing with horizontal asymptotes, is I'm going to factor out the bottom. Two numbers that add up to 8 and multiply out to 15 are going to be 5 and 3. Now, this is what I have. Okay, this is what I have so far. I have what appears to be right here, two vertical asymptotes. However, this picture here tells me that I only have one vertical asymptote, and it lives at -3. So you are a vertical asymptote. I do not have a vertical asymptote at 5, which is telling me, I'm sorry, -5, -5, which is telling me that I'm probably going to have a hole there. So that's going to be x plus 5 up there. Okay. Also, I have a 0 at 3, which tells me I should have a x minus 3 up here. So when I factor the top out, because all I really care about is the top, when I factor the top out, or FOIL rather, I get x squared minus 3x plus 5x minus 15. Combine those guys and you get x squared plus 2x minus 15. B is 2. So B is 2, and B is my answer. The graph of a function f of x displays the following behavior near x equals 0. It's a little hard to read this, so let me just rewrite it out here. The limit as x approaches 0 to the negative means you're traveling from the left side. So traveling from the left side. That's going to be the same as the limit as x approaches 0 positive, which means from the right side, and both of those equal infinity. Now, graphically, what this looks like is I don't know 100% of what's going on as far as my graph and what it looks like, but if it's going towards 0 from the left and shoots up to infinity, and the right side has to do the same, it's got to look something like that. Now, 1 over x is a function that looks like this, so it's not going to be a. 1 over x squared looks like this. Okay, there's a rule that it says if you have like multiplicity stuff going on, you're going to go to the same exact infinity depending on whether things are positive or negative here. And since we have 1 over x squared and x squared's in the denominator, we have both sides going to the same exact limit, which is infinity. Okay, so definitely not you, because it's definitely you. Consider the function below. F of x equals x minus 2, x minus 1 over, x minus 2 again, x minus 3. Which of the following statements I give up, describes a feature of this function? So let's talk about holes and asymptotes. So before I even look at the options, let's see hole, asymptote. What we have is, since upstairs and downstairs are the same exact thing, that tells me that there is a hole at the number that makes this factor 0, and the number that makes that factor 0 is 2. 2 minus 2 is 0. I have a vertical asymptote then at the number that makes this bottom one 0 at 3. I have a 0 at 1, but I don't have to worry about that. So there is a hole at x equals -2. Nope. There is a hole at x equals 2. Yep. There is an asymptote at x equals -2. Nope. There is an asymptote at x equals 2. Nope. 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 Nope, 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 nope. Like and subscribe. Consider the function below. Which of the following statements correctly describes a feature of this function? So asymptote, hole, asymptote. So obviously what it wants me to do is figure out my holes and asymptotes. Now before I do that, I need to factor each guy out. So this is quadratic stuff, so I know it's going to look like this on the top, and it's going to look like that on the bottom. So up top, I have two numbers that add up to -7, multiply out to regular 12. So x minus 3, x minus 4 should do the job. Two numbers that add up to -4, multiply out to +3 should be x minus 3. Ooh, look at that. And x minus 1 should do the job. A hole exists when you have a factor in the denominator that's the exact same and the exact same amount as a factor in the top. So a hole exists at the number that makes that factor 0, and 3 minus 3 is 0, so the whole happens when x is 3. A vertical asymptote exists when you have a factor on the bottom that is not repeated up top, and whatever number makes that factor on the bottom, 0, is going to be my vertical asymptote, so x is 1. X minus 4, what would that give me? That gives me a 0, but I'm not worried about that because I'm only worried about asymptotes and I'm worried about holes. And so I have a hole at 3, not an asymptote at 3. I have a hole at 3, yup. I have a vertical asymptote at 1, nope. And a vertical asymptote, or an asymptote, it just says asymptote. I'm assuming it means vertical, but none of these are true. So there you go. There you have it. Pretty simple. Consider the function below. We've got ourselves quadratic over a quadratic. Where is there a hole in the graph? Well, let's factor this stuff out. That's the only way we're going to be able to do it. So quadratic upstairs is going to look something like this. I need two numbers that multiply out to -4 and add up to -3. So -4 and +1 should do the job. I'm going to do the same thing. I'm going to factor downstairs. So I have two numbers that multiply out to 3 and add up to 4, so 1 and 3 should do the job. They want a hole. A hole exists when you have a factor on the bottom that's the exact same and the same amount as the factors that you have up top. X plus 1 on the bottom and x plus 1 on the top are the same. Now, the hole exists at the x value that makes the factor equal to 0. So -1 plus 1 is 0, so x is -1 is going to be my hole. A rational function f has a hole with coordinates -1, 7. Which of the following equations could define f? Now, when it comes to holes, I only care about the x value. And a hole exists when you have, and in this case, when we were to factor stuff out, if we were to get something like x plus 1 on the bottom and x plus 1 on top, that's going to be a hole. First things first, you have to have the same amount of factors upstairs that you have downstairs, and they have to be the same. Now, why did I choose x plus 1? Well, because the hole exists at x equals -1, so the factor created by a hole existing at x equals -1 is going to be the opposite of that because it would make the factor equal to 0. So what I have to do is I need to take turns factoring all three of these guys and see which one looks something like this. Any repeats and not a repeat kind of breaks the whole thing apart. So this is a quadratic. Two numbers that add up to -5 and multiply out to -6 are going to be -6 and +1. So it starts out somewhat promising. If I factor out an x, that leaves me with x plus 1. So I have an x plus 1 up here and an x plus 1 down there. Nothing extra to throw us off. 1 is an option. All right, let's try it again. Let's factor that guy. Two numbers that add up to -4 and multiply out to -5 are going to be x minus 5, x plus 1. I can factor out a 6. That leaves me with x squared plus 3x plus 2, which continues factoring out to 6 times two numbers that add up to 3, multiply out to 2, x plus 1, x plus 2. Up here we had x minus 5, x plus 1, x plus 1 up here, x plus 1 down there. No repeats of any of those. 2 seems to do the job. Now let's see if 3 will do the job. Let's factor out the top. Two numbers that add up to 7 and multiply out to -8 are going to be x plus 8, x minus 1. We could stop right here, but I'm going to keep going. Two numbers that multiply out to -2 add up to positive invisible 1 are going to be x minus 1, x plus 2. Or do I have that backwards? Nope, I'm good. Now, x minus 1 is not what I want. It's the opposite of what I want. So the hole would exist at 1, so it can't be u, which means it can't be u, which means it must be u. Let p and q be non-constant polynomials such that p times q is that guy. If p is an odd degree polynomial with a leading coefficient less than 0, determine the end behavior of q. All right. What's important here? You're my leading coefficient. So right now, P times Q is negative 9Q, or X to the 8th. It's telling me that P is an odd degree polynomial. Okay. So P is an odd degree polynomial, so I'm going to divide out essentially because they want me to get Q all by itself. I'm going to divide out an odd degree, so let's just make one up, X to the 5th. And the leading coefficient is less than 0, so negative, who cares, X to the 5th? It could be X to the 3rd, it could be X, it could be X to the 7th. It doesn't matter because Q is going to give me n behaviors that I want anyway. So if I just do this, Q is going to end up being positive X to the odd, whether it's X to the 5th, X to the 3rd, who cares? Either way, the left side looks like that, the right side looks like that. So the limit as X approaches negative infinity is also going to be negative infinity, and the limit as X approaches regular infinity is going to be regular infinity. So infinity is infinity, negative infinity is infinity, no. Infinity is negative infinity, no. Infinity is infinity, negative infinity is negative infinity, yep. And no. Okay, so kind of a weird problem. This is where, they kind of step away from a standard typical problem and really make it feel like an AP exam, but we did it, and I feel great. The rectangle above has an area of, that quartic, and a width of x plus 3. Determine the missing length of this rectangle. All right, so if the area is that quartic right there and the width is x plus 3, in order to find the area, I do length times width. So what I need to do is I need to divide x plus 3 and make sure that is in order and there's no missing spaces in between, so I am good. Oh, this is going to be fun. Now, a lot of people might look at synthetic division and do synthetic division, and there's absolutely nothing wrong with that. In fact, it's arguably faster. So if you know synthetic division, go ahead. It's going to end up being the same exact thing anyway at the end of the day. X times what gets me 3x to the 4th? 3x cubed does that. So multiply 3x cubed to x, 3x to the 4th. Multiply 3x cubed to 3, 9x cubed. Oh, how about that? Now we subtract this entire row, which involves us flipping the signs. You will always go away, and you actually become 0. So drop down the positive 2x squared, and since this became 0, drop down the regular 7x, and then we kind of, skip a step a little bit, because that's 0. X times what is 2x squared? X times 2x is 2x squared. So multiply 2x to x and you get 2x squared. Multiply 2x to 3 and you get 6x positive. Subtract that entire row, which means flip the signs, flip the signs. 7x minus 6x is going to be regular x. Drop down the plus 3. X plus 3 times what is x plus 3 plus 1? So the guy that I get is going to be positive 3x cubed plus 2x plus 1, which is C. So regular polynomial long division disguised as a rectangle area problem. Kind of tricky, but tons of fun. The function a of x is equal to c of x over x. If a of x has a slant asymptote, which of the following equations could represent c of x? All right, so a of x has a slant asymptote. It's being divided by x. The only way you can get a slant asymptote is if your leading coefficient for c of x is x squared because it's 1 degree higher. So the numerator has to have 1 degree higher than the degree of the denominator, and so whatever x squared has to do it. So C is linear? No. B, yep. You're cubic? Nope. You're cubic? Nope. So B is the only guy because this would give me a slant asymptote. Fun, fun. Which of the following is the third term of the expansion 2x plus 3 all of which is to the fifth. So, all right, this requires Pascal's triangle. All right, so zero term or 0 degrees. So if the degree is 0, you have 1. If the degree is 1, you have 1, 1. If the degree is 2, you have 1, 2, 1. So now what I'm doing is the outside is always going to be 1, and then the inside is always going to be the sum of whatever these guys are. D3, so I'm not even close to what I want to be, which is D5. I have 1, 3, 3, 1. D4 is going to be 1, 4, 4. Nope, 6. 4, 1. And then finally D5, 1, 5. Let me do this. Let me make you a special color because we care about the third term. 10, 5, 1. You basically set this guy as your A, set this guy as your B, and you kind of go along with the motions. So like D5 is going to be, A to the fifth. 1, I guess I should say 1A to the fifth, plus 5A to the fourth, B. And then here's where it gets very important, plus 10A to the third, B squared. Now I can keep going, but I don't need to. What I'm going to do is, since I already labeled A 2x, I'm going to replace A with 2x. And since I have B as 3, that's going to be 3 squared. So 10 times 2 times 2 times 2 times x times x times x times 3 squared becomes that. And then you get 80 times 9, which is 720, times x to the third gives me A. So I kind of feel dumb. I could have just noticed that immediately because it asks for the third term of that expansion. So A, I could have done like right away if I just would have realized that that's the only cubic one there. But, I did the whole thing kind of, and I'm glad I did. Ooh, we've got ourselves a calculator problem. Mathematicians at a water purification company have created a function that models the cost C of removing P% of the impurifications from 1,000 gallons of water. The function is gross. Evaluate and interpret P, or the limit as P approaches 100 from the left of CFP in the context of this problem. So clearly we're going to want to use a calculator for this one. So I'm going to take a step aside and take a look at what the calculator has to look like. Okay, let's graph this gross, terrible problem. Let's hit y equals negative. Don't make the mistake of typing out minus sign. They mean different things according to TI. 0.1 x squared plus 32 x plus 1043, close your parentheses, and divide that by parentheses x minus 100. Now, we care about what happens when x approaches 100. So if I graph it, I'm not going to see at all what I need to see because we only go out to 10. So let's do this. Since I care so much about what happens at 100, let's make a window going from 50, that's 500, 50 to 150, just for funsies. Okay, this is rational, so I kind of probably need to give myself a nice big window. And that didn't seem to do it. So let's zoom out. Zoom 3. Enter. No. So let's zoom out again. Zoom 3. There we go. All right, so there's 100 right there. See how it's blinking 100? What the question is asking us is the limit as p approaches 100 with the little negative symbol. That means from the left side. So if I go from the left side, knowing very well that I have a vertical asymptote at 100, from the left, I shoot up right to 100. So that's the graphical interpretation of what this problem is. So let's go back to the actual question and see if we can answer it. All right, so according to the picture that we got, we have this rational looking thing where magic happens at 100, which makes sense because at 100, bad news happens. We care about what's happening coming from the left side. So coming from the left side, we go up to positive infinity. So looking at all of our options here, no, no, yes, no, and here's why. The company will pay more as they remove more impurifications and will never remove 100%, which makes sense. You're never going to remove 100%. So that's what we get for this one. Kind of a tricky problem, very strange indeed, but we did it. The function f of x equals x minus 3 in parentheses squared plus 6, and it is translated 7 units left and 4 units up. Whenever you translate 7 units left, what you do is you go inside the parentheses where you see x, and even though it says left and you're thinking, oh, left is negative, you actually add 7 inside the parentheses. Yeah. And when you go 4 up, you add outside the parentheses. So given the fact that we were given this information right here, x minus 3, we're going to add 7 to that x minus 3 and end up with x plus 4 squared. We're going to add 4 to 6, making that 10. And at the end of the day, g of x, which is what we're trying to find, is going to be x plus 4 in parentheses squared plus 10, which is b. The table provides the values of the quadratic function f of x. Given g of x is defined as g of x equals negative 3 times f of x plus 4. What is g of 4? Well, I need to find g of 4, so let's do this. F of 4 is going to be this guy, or rather g of 4 is going to be that guy where I substitute 4 in for f of x. So let's do negative 3 times f of 4 plus 4. F of 4 is 34. So negative 3 times 34 plus 4 is going to be negative 102 plus 4, which is negative 98. So kind of strange and not near as complicated as these translation problems have a tendency to be. I like it. Let f be the function defined by f of x equals negative 2x to the third. The function g of x is created by the following sequence of transformations: a vertical dilation by a factor of 2, then a horizontal translation, and then a vertical translation. So let's go in order. Step number 1, a vertical dilation of the graph of f by a factor of 2, which means we are going to, so far, g of x is going to equal 2 times f of x. Vertical dilation has you multiply 2 to the entire thing. So far, what we get is 2 times f of x is 2 times negative 2x to the third, which is negative 4x to the third. Now that's step 1. Step 2 has us taking a horizontal translation 3 units right. When you take something and go 3 units to the right, you open up the parentheses for everything attached to x. And what you're going to do if you're going to the right, when you deal with horizontal translations, it's backwards land. So 3 to the right is not plus 3. 3 to the right is minus 3. So x minus 3 cubed. Last but not least, and probably the easiest part, is we're going to take this guy and move it 2 units up. So all we do all we do is just add 2 outside of the parentheses. So negative 4, x minus 3 in parentheses, cubed, plus 2 happens to be C. So not a pleasant problem. I hate these personally, but hey, we got through it, and I had a great time. Let f of x be a function with a domain between 0 and infinity, and a range between negative infinity to 0. Oh, I hate this already. So let's draw a picture. And we'll let f of x be red. Domain is 0 to infinity, which means to the right of the y-axis, and the range is negative infinity to 0, which means up to the x-axis, so smiley face. There you are. Oh, not bad. You got a weird-looking eye there, but I like him. He's my friend. He's the only friend I have. Find the domain and range for g when g is 4 times f of x, which means it's super stretched out, minus 2, and then the x is negative. Ooh. All right. So first thing we need to look at when the x is negative means we take this guy, flip him left to right. Okay? That is called a horizontal shift. When you negative x inside, you just flip it left to right. It's a mirror image left to right, as opposed to flipping up and down. So this is a mirror image. So of course, if you had like an eye patch, the eye patch would live here, but that doesn't really matter in this context. If you multiply it by 4, you are stretching him up, okay? So he's actually going to go down here a little bit. And if you minus 2, he's going to go down a bunch. So let's move this poor guy's face. Okay. And then the extras, and then the extras, and then the extras. So what we have is basically this green guy lives between negative infinity to 0 on the domain. So not you, but these two guys are still good. So the range is where it gets iffy. The domain has to peak out at 0. So if I plug in 0 for x, it'd be nice if I had a marker. If I plug in 0 for x and I multiply 4 to 0 and then subtract 2, that becomes 0 minus 2. That becomes minus 2. So my range starts at negative 2 and goes down forever. And the only one that has that as an option is C. So a very tricky problem. My suggestion is if you're like, I really hate this and I hate it a lot, then try plugging in domain values and see what happens to your answer. And when you plug it in here and take it from there. Kind of an iffy problem. Don't like it. A t-shirt is launched straight up into the air from a cannon with an initial velocity of 50 feet per second. From a height of 4 feet, the height of the t-shirt can be modeled by this function right here. Man, it sounds like we're at a baseball game or something. Good old t-shirt cannon stuff. T is time in seconds. T-shirt's launch, blah, blah, blah. Which of the following is a true statement? So we have ourselves a quadratic. It's going to look like this. Okay, and what I need to do is I need to use this information to run to a calculator and find out which of these statements are true. So be right back. All right, so we got the old traditional launching t-shirts in the air type problem. So let's go to y equals and type it out. This is a very typical gravity equation. When you see that negative 16x squared or t squared in this case, x squared is the same thing, that tells you gravity. Then you have plus 50x, and that plus 4 means that you're 4 feet in the air when you launch this out. Okay, that would be your y-intercept, which means at 0 seconds, you're 4 feet in the air. When I hit graph, I'm not going to get a whole lot. See? So what I need to do is I kind of need to figure out where some of my major numbers are. Looks like we start at 0-ish. And after 1, 2, 3-ish, we hit the ground again. So t-shirt's in the air, comes up, goes back down after about 3 or so seconds, hits the ground again. So what I want to do is I'm going to create a window that gets me better x values. So I'll do -1, because I Can't just completely let go of the past. And I'll go to 4, and I'll hit the graph, and at least I have a good indication as to where I begin and where I end. Now, looking at the 4 options that I have, option A says the t-shirt will reach a maximum height of 50 feet, approximately 1.875 seconds after launch. So and looking at these, the height is always going to be, looking at B, the height's not going to go any bigger than 50, it looks like. So I'm going to go back to my window. I'm going to change my Y max to 55 because I'm expecting it to peak out around the 50s. And the Y min, I can leave it like 0. I'll make it -5 just to have some underground stuff going on. And when I hit graph, I get a much better visual. There you have it. Now, A says the t-shirt will reach a maximum height at 50 feet at 1.875 seconds. So I need to make sure that whatever this guy is, it happens at exactly 1.875. This is my maximum. So I'm going to hit second, trace. I care about my maximum, so I'm going to either hit 4 or go to 4 and hit enter, and I need to calculate my maximum. So my maximum's right around here. I'm going to go to the left of it, hit enter for my left bound. I'm going to go to the right of it, moving, and now I'm going back down. So my maximum's going to be in between those 2 lines right there. Hit enter, and my maximum happens at 1.5624, and the maximum is 47 or 43. So that's not A at all. That's actually B. And B says the t-shirt will reach a maximum height of 43 feet. So 43, yeah, close enough. And it happens at 1.563, which when you round that or whatever, it's close enough. There's a little bit of wiggle room with these. So yeah, my guy is actually not A, it's B. And if you look at your picture, C and D don't even make any sense. That is just crazy talk. So my answer for this guy is going to be B. It's going to be Bay, as one time Justin Timberlake once said. Remember that song? Okay, back to the problem. And I'm back. And when trying to see if A was true, it ended up B was true. So yeah, kind of you didn't have to show any work there, not a lot of craziness, just, throw it in your calculator and click a few buttons and the answer is B, it's not A. The value of stocks on the market typically fluctuates over the course of a day. Now, suppose a particularly volatile stock's daily value can be modeled by this terrible function where H represents the hours after the stock market opens for early trading. The stock market is open for 9 hours, so the domain is that. That's going to be helpful because we're going to have to throw this into a calculator. Approximately how many hours after opening does the stock reach its lowest value? So I don't know what this guy looks like. It's a quintic. So at some point, I'm expecting this to happen between 0 and 9. And what I'm going to do is I'm going to try to throw that in my calculator and find out what that minimum value is and what it represents to in this real world problem over here. All right, so we have this terrible equation to plug in. So, we're just going to plug it in and make sure that instead of H, we use X and just go from there. So X to the 5th minus 20X to the 4th. Move to the right. Plus 146X to the 3rd. 1, 4, 6. X to the 3rd minus 484x squared. Probably should have typed this in ahead of time. That's all right. The more time that I have on screen, the more money I make. Sweet YouTube money. Plus 717x. It's the Lancaster area code. And then last but not least, we get 15. All right, it gives us a domain of 0 and 9. So what I'm going to do is I'm going to go to my window, and I'm going to choose my window. Instead of using 0 and 9, I'll give it some wiggle room, -1, and I'll leave that at 10. So let's hit graph and see what we have. Terrible. Absolutely terrible. Now here's why it's absolutely terrible. These numbers are huge. So let me set my window. I have a couple 700s. Let me actually look at my, see, I was hoping that if I look at my answers, it would give me a good idea as to what numbers that I have that are super big. Why don't I hit zoom out and just keep hitting zoom out until I see things either bottom out or, and that's what I want to see. I want to see it bottom out because it asks that question. It wants it to reach its lowest value of the day. So I need to see the bottoming out. Don't see that. So zoom out again. Zoom 3, enter. I don't see much there. Zoom 3, enter. Ugh. Zoom 3, enter. Yeah, this just ain't good. What if I set my window now that I know what I know? Let's set that window back to 0, or better yet, -1 and 10. Maybe that gets me a much better picture. Let's see, graph. Look at that. So sometimes you just have to play around with the calculator a little bit. It looks like whatever this number is, give or take, is going to be my minimum. So I'm going to hit second. And just because I need to find the minimum between 0 and 9, let's do the minimum between 0 and 9. So let's go all the way over to 0, all the way over to 0. Or is it? Yeah, 0 and 9. So I'm going to go to 0. Perfect. Enter. I'm going to go all the way to the right side to 9. I probably didn't need to zoom out to do this, but at least I got a nice looking picture. Boom. And my minimum, which I thought maybe would be at 0, is actually not at 0 at all. My minimum is at the x value of 7.11. So approximately how many hours after opening does this stock reach its lowest value of the day? 7.11, 711, is much, much, much closer to 7 than it is to 8. So we are going to say that C is the answer we're going with for this guy right here. So after doing all of that, the lowest value was 7-point-ish. So we said that's close enough to 7. So, tricky problem. The biggest mistakes that are made is just typos. You just have to be careful. The volume of a spherical water balloon can be calculated by the formula V equals 4/3 pi r cubed, volume of a sphere. A variety pack of water balloons contains balloons that, when filled completely, the range of the volume is from 65 cubic centimeters to that cubic centimeters. Which of the following measurements would be inappropriate for the minimum and maximum diameter? So this is a calculator section, and the reason why this is a calculator section is we have pi, we're going to have the cube root. So what I'm going to do is I'm going to run to my calculator, and I'm going to try to find out what happens when I replace V with 65. So I'm actually going to do the whole thing straight on my calculator, knowing very well that my first step is going to be dividing by 4/3 pi on both sides. So I'll run to my calculator, see what happens when I do this. That will give me one of these options. And once I have the other option, I'll probably go a different route to see if the other option is the correct option. So I'll be right back. Okay, so this problem right here, we're basically using our calculator to do the heavy lifting for us. There's two ways that you could approach this. You can plug in your answers and see which one gives you what you want, or you can go backwards, which is what we're supposed to do, and I'm going to go backwards. So I need to test out a volume of 65. And so if V is 65, in order to get R cubed by itself, I have to divide out 4/3 pi. When I do that, I'm going to use more parentheses than may be necessary. And actually, I don't think it's necessary. That double parentheses seems off-putting, but trust me, more parentheses is useful. I don't want to make the calculator believe that pi lives in the numerator or whatever. That's the guy I get. Now, R cubed equals that. I need to take the cube root of that, and I take the cube root by hitting Math 4, which is the cube root button. Don't feel like typing that number in, so I'm going to hit second, negative symbol, and the cube root of that gets me 2.5 basically. Now my radius is 2.5-ish. They don't want a radius, they want a diameter. So in order to find the diameter, I'm going to multiply U by 2. And so the diameter that would give me a water balloon of 65 centimeters cubed would be 5 centimeters, which gives us our answer right away at B. Now I'm paranoid, and I want to make sure that I did it right. So let's do this. Let's go forward this time, or backward, or however you want to view it. Let me test to see if B is correct by using the maximum diameter of 10. So what I'm going to do is I'm going to plug in a diameter of 10. So if by plugging in a diameter of 10, 4/3 pi, here's the pi button. If the diameter is 10, I'm not going to use 10. I'm going to use 5⁵. Now, if all goes well, it should get me a number awfully close to 524, which it did. So my answer is definitely going to be B, and I made sure I did it right the first time, and I just kind of double-checked using the second route. Fun. And I'm back, and it looks like it is B. So kind of, you have to be careful. The whole thing that throws me off is the diameter phrase. So if you're not careful with the diameter, it's going to blow up in your face, much like this water balloon. Hee hee. Like and subscribe. Bella and Jose each toss a baseball at the same time. I wonder if it's the same Bella from Twilight. Probably. They're talking about baseball. Remember that scene where they're really fast? The height of Bella's baseball in meters is modeled by the function b of t, where t is time in seconds since they threw the balls, and they're talking about height is meters. Great. The height of Jose's baseball is modeled by j of t. Makes sense. That's his letter. Also measured in meters, t is in seconds. And then it tells us this, that j of t is equal to b of half of t. Now notice that they're the same thing, except for t is now being halved. So what's going on when you take a number, when you take t and you half of it, you have what's called a horizontal dilation, where maybe j of t, right, the regular old equation is going to look something like this, right? He throws the ball up. By taking half of t, and this is where it gets really weird because this is translation stuff, and this is where horizontal translations or horizontal dilations are not fun. Whenever you do a horizontal dilation and you change f of x to half of something, we view it as x over a, where a gives you that dilation. Since b is 1/2 t, 1/2 t is the same thing as saying t over 2, which means in this case, a is over 2. So Jose's flight path looks like this. Bella's flight path is going to be a horizontal stretch. The height won't change, but the time that it takes to hit the ground will. So the height from which Jose tossed this baseball was exactly half of the height? No. The height from which Jose tossed this? No. The maximum height of Jose's baseball was exactly half? No. It took Jose's baseball twice as long to hit the ground? Yes. Okay, so it's not the height that changes, it's the time and that it takes to go from up and down that changes. So very tricky problem. And if you're like, man, I really don't know what to do, then just, kind of plug in T and see if you can create your own type of problem. But, Jose and Bella, Twilight Princess. When t is equal to 0, there are 2 cups of waffle mix in a bowl. Water begins to be added to the waffle mix in the bowl at a constant rate r cups per second. For time is positive, makes sense. The percentage of waffle mix in the bowl is given by the function p. Write the expression for p when t equals 5. Okay, so this is how I'm going to set this up. Don't like these problems, don't like them at all, but this is what I'm going to do. At the very beginning, you have 2 cups of waffle mix, dunzo. Now what's going to happen is you're going to create a total. So when I think of this, I almost think of probability where you have what you want over the total possibilities. So now what we're going to do is we are going to add a certain amount of water to the mix. So if we were to add what are we dealing with? Cups. So if I were to add half a cup, I would have 2 plus a half. Now I don't know how much I'm adding. All I know is that I'm adding for 5 seconds and I'm adding at a rate of r. So it's going to be 2 over 5 times r. So whatever the rate is, if it's half a cup per second. That doesn't make sense. Like a tenth of a cup per second. I'm going to have 2 cups of waffle mix, and over here I'm going to have waffle mix plus water. And the way I figured out water, it's going to be 5 seconds of whatever rate this is. So that translates to U. Okay? Translates to U. And so the percentage is going to be calculated at 2 over. And if I were to be 5, the rate is whatever, and I end up with 2.5, half a cup of water. Now what I have is 80% waffle mix, which is what they want. They want a percent P. So P would equal 80. So I'm not going to add the 100s there. I'm going to leave it at that D. The table above shows wind speed in miles per hour and the amount of electric power in watts produced by a wind turbine for the interval 0 to 50. Boom, boom. Okay, I don't have 50, but I have that much. Using regression, find the equation of a third-degree polynomial. Third-degree polynomial regression is cubic regression. So I'm going to do that in my calculator. And then what I need to do is I need to find out what happens when I plug in 50. So I'm going to do cubic regression and then plug in 50. And when I do this, I'm going to find out that the cubic regression isn't pretty, and there's going to be a little shortcut that we could use to make life easier. Cubic regression. So let's start by hitting Stat, Edit, and just typing away. We've got 0, we've got 11, we've got 18, we've got 24, and we've got 28. You move to the right, we've got 0, we've got 1.2, we've got 5, we've got 12, and we've got, last but not least, Brian Dawkins, 20. Now, I'm going to make believe that I don't already know what's going to happen, and I'm just going to do the whole cubic regression thing. Second quit, and I'm going to hope and pray that my answer is lovely. So I'm going to go to second quit, I'm going to go to stat, I'm going to go to calc, and I'm going to go to 6 cubic regression, calculate, enter, and gross. Okay, pretty bad, isn't it? Now, my goal is to find out what happens when I plug in 50. I really don't want to have to type any of this out and plug in 50. So let's pretend that I didn't do cubic regression. Let's hit the rewind button. That's me hitting a rewind button. It's a sound effect. Now, I'm going to pretend that I'm doing this all over again, blah, 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 blah. I'm going to second mode. I'm going to quit. I'm going to go to stat. And I'm going to assume that my equation is going to be bad. I'm going to go to cubic regression. Now, if I'm going to plug in 50, what I want to do is I want to store this formula into y equals. And so this is what I'm going to do. I'm going to go to store reg eq, which means regression equation. I'm going to go to vars. I'm going to hit right to y vars function y sub 1. And what this is going to do is this is going to store my equation in y sub 1. So now when I go to calculate, it gives me that terrible answer again. But when I go to y sub 1, there it is. So hitting graph isn't going to do a whole lot for me. But what I can do to find out what 50 is I can expand my window to 50, or I'll go 51. I'll go one step further. Okay. When I hit my graph, there it is, way the heck up there. I don't see it, but I really don't need to see it, because what I can do is I can hit second, trace, and go to value, which is 1, and type out 50. And when I do that, I have 129.27142, which is awfully close to 129 watts. So we plugged in the value of 50. If you have all the patience in the world, you could have done second table and gone down to 50. But, that worked. This worked for me, and I lost it. But, what we saw here, in addition to doing cubic regression, is storing our equation into y equals. And once again, if you missed that, you hit stat, you hit calc, you go to whatever regression that you're doing, and when you type it in, you go to store regression, vars, y vars, function, and you store it into whatever equation that you need to, so that when you hit enter, it's there. Okay? All right, let's circle C and call it a day. And we're back, and we got 129 watts. So, yeah, that's that. The number of cars in a parking lot is modeled by the function c of t, and then you're given a table of values to figure that out. If the rate of change of c of t on the interval 2 to 8 is equal to the rate of change of c of t on the interval 2 to 5, find the value of k. Okay, so here's k. So this is what I need to do. I need to find the rate of change from here to here. So the rate of change is found by using the formula. And average rate of change, same thing. It doesn't tell us anything about whether this is linear or not, but that's fine. We don't need to. Average rate of change is the slope formula. Average rate of change does the same thing. So there you have it. A and B are going to be my intervals, so I can call you A and I can call you B, which makes you f of A, which makes you f of B. So I've got 50 minus 40 over 5 minus 2, which is 10 over 3 gross. Now, my average rate of change is 10 over 3. They want me to find k, knowing that from 2 to 5 is the same as 2 to 8. So now that I know that my average rate of change is 10/3, I'm not going to do patterns, not going to do it. I'm just going to solve for an equation. I'm still going to bring this back. Okay, I have f of b minus f of a, where now if I erase all this information and my job is to find from 2 to 8, I'll call you A and I'll call you B, making you f of A, making you f of B. So f of B minus f of A is going to be k minus 40 over b minus a, which is 8 minus 2. What do I know about this average rate of change? Well, it's the same as u, which means it's going to equal 10/3. So let me kind of write the problem over here, continue the problem over here. K minus 40, nothing I can do about that. Over 6 equals 10 over 3. We have a proportion, so crisscross applesauce means I multiply u times u, so 60 is going to equal u times u, so that's distributive property. 3 times k is 3k, minus 3 times 40 is going to be 120. If I add 120 to both sides, 180 is going to equal 3k, and divide by 3, k is going to equal 60. Okay. And you would look at this and say, well, hold on, wait a minute. That's kind of weird because we went from 40 to 50 to 80. This big jump kind of screws things up. And that's why it went back down to k, because we're dealing with average rate of change and stuff like that. So there you have it. That should do it for all of Unit 1, all of these random math problems I found on the internet. Oh, man, so many.